Well, good afternoon, everybody. And as you're enjoying your lunch, thank you for joining us here at Flight Research for our presentation this afternoon. We're very, very happy to have you here, and I hope that you get something out of this presentation. We'll have some questions and answers for you at the end, or questions and answers as we finish, and we have some mics we'll pass around and so forth. But I want to talk about a subject today that is of growing concern in the aviation community. It's a growing concern among the NTSB, the FAA, insurance companies, leading aviation institutions, as well as us at Flight Research. And the issue is loss of control accidents now account for more passenger deaths and aircraft accidents worldwide than any other single cause. Not loss of flight into terrain, not mechanical, not weather, things that used to cause aircraft accidents, no longer. It's loss of control in flight. This is a very, very serious situation. And what I'd like to do today is explore some of the reasons behind that by looking at a couple aircraft accidents, by looking at some of the STB results of those accidents, to try to determine what the common threads were. Why did these accidents occur? More importantly, as we determine the common threads, what can we as an aviation industry do to try to prevent these from happening again? I was talking to some gentlemen just before the presentation began, and you know, believe it or not, I took my first solo flight in 1965. So I hate to give away my age, but that's how long I've been flying airplanes, 1965. I'm still around, and I've had a lot of scares. But one of my passions in life has been aviation. And I would like to think that as we grow older as a generation of aviators, that aviation has given us so much that we can give some things back to aviation in terms of improved safety. And that's really what I hope we can do at Flight Research with our upset recognition and recovery training. The interesting thing about all of these accidents, these loss of control accidents, is that the aircraft was flying along. The flight crews thought they were going to have a great day. The aircraft was structurally sound and mechanically sound, and all of a sudden, they hit an in-flight condition which caused a sudden, alarming upset. The crew got confused, the crew was fearful, the crew didn't recognize what was happening, did the wrong thing, and they lost the aircraft, and they lost the passengers that were in the aircraft. Now, what is loss of control? Well, to put it simply, the way the NTSB defines it, control upset is a situation where the flight crew fails to maintain control of a structurally and mechanically sound aircraft in an upset situation. The NTSB will tell you that all loss of control accidents should have been preventable, and yet they were not, because the flight crews did the wrong thing at a critical time during the upset scenario. To look at the statistics, and this is the worldwide jet fleet, basically the air carrier fleet. There's been 18 accidents and 1,850 fatalities in the last 10 years. Some of the more important ones or recognizable ones you probably have heard about: Cogon 3407, Air France 447, American 587, et cetera, et cetera. But even more of a concern, if you look at the general aviation community, which includes the Part 91 folks, a lot of you are Part 91 folks in this room, the number is almost 7,200 accidents and about 1,368 fatalities. To put it in perspective, just about every day there are 2 accidents every single day that are loss of control oriented accidents caused by loss of control. Some of these you don't hear about because it involves a couple of passengers, a pilot, and it doesn't make the headlines. Others, of course, you hear about when the loss of life is greater. Interestingly enough, in the Part 91 world, the first 6 months of 2014, the accident rate has been almost double what it was in the same period as 2013. So this is a trend that is getting worse, not better. What I'd like to do, not for the sake of disparaging the airplanes that were involved, the flight crews that were involved, or the airlines that were involved, I'd like to take a look at a couple of accidents that we could sort of analyze and determine what happened and why these airplanes were lost. And by the way, we've done research on a whole bunch of these, and I could have picked any 2 or 3. The scenario is pretty much the same, but this will give you more of a sense of what occurs in the flight deck during the time these accidents occur, because there's a lot of commonalities here. Call gun 3407 we've all heard about. It was a Bombardier Dash 8 Q400, was flying into Buffalo, New York. Now, there were some issues with the crew fatigue and so forth that played into this accident. There was also a very significant issue about what the flight crew thought was the proper VREF on final. Flight crew made a mistake when they programmed their computer to give them the VREF speed because they didn't include the possibility of icing, and yet icing was prevalent in the area. When they turned the anti-icing system on, the anti-icing system said to the flight control system, set the stick shaker at a higher level. So the flight crew was not expecting that. They didn't program the computer to tell them that, so they weren't expecting it. Nevertheless, that wasn't the major cause of the accident. They were with approach control, and the pilot slowed the aircraft down to 131 knots. At 131 knots, the stick shaker actually went off. And the pilot's reaction to that stick shaker going off was to, as he was taught in the simulator, by the way, to apply full power and pull back on the control yoke. Why was he taught to pull back on the control yoke? Because the NTSB report will show you that when they were trained in the simulator, they were taught that losing more than 100 feet of altitude in the simulator during a stall scenario, you would bust the ride. So you were taught to maintain altitude at all costs. So the reaction was full power, back on the control yoke. Now the aircraft at 131 knots had not stalled. It was still flying. But when the captain pulled back on the control yoke at 131, he increased the G loading to 1.4, the airspeed slowed down to 125, and the angle of attack went up to 17. And then the aircraft stalled. The aircraft started to roll. And by the way, in the voice recorder, when you talk about panic and fear and startle, all those emotions, they absolutely had no idea what was going on, and they were scared. You could hear it in their voice. The airplane started to roll. Now, this airplane has a stick pusher device, which you know will help the pilot aerodynamically recover from a stall by automatically pushing the yoke forward to help with that aerodynamic recovery. During this rolling process where the aircraft was fully stalled, the stick pusher went off the first time, and to counteract the stick pusher, the pilot pulled back with 90 degrees of force on the control yoke to counteract it. Stick shaker went off, stick pusher went off again. The pilot countered with 160 degrees of force on the control yoke to counteract it. The aircraft went in, killed 49 people in the airplane, 1 person on the ground, 50 dead, airplane totally destroyed. Question is, why did this pilot do exactly the opposite thing he should have done relative to the stall regime and departure situation that he found himself in? Well, the NTSB said that he was improperly trained in the proper stall recovery techniques in the simulator. Icing was not a factor. So he tried to do what he was taught in the simulator in the aircraft with catastrophic results. Air France 447. We've all heard of this one too. This was an Airbus 330, and it was flying over the Atlantic at 38,000 feet. Very cold night, visible moisture. They actually got into some turbulence, and the pitot tubes on this aircraft iced up, and the crew got unreliable airspeed indications. Now, the captain wasn't on the flight deck. There were two co-pilots actually on the flight deck. One in the right seat was the junior guy, and the one in the left seat was the more experienced guy. When the airspeed indicators became unreliable, the autopilot kicked off, and the co-pilot in the right seat said, "I've got the controls." Now, we know that in the Airbus there's a complication with the way these side sticks work because they're not coordinated. In other words, the last one that puts the input in is the one that controls, and you can't tell between the two who's doing what. But in any event, the co-pilot flying the aircraft on the right side said, "I've got the controls." His reaction was to leave the power exactly where it was, and again he pulled back on the control stick, and he stalled the airplane. The aircraft angle of attack when he pulled back on that yoke was about 17 degrees or so, fully stalling the aircraft at 38,000 feet. That airplane stalls in a pitch-up attitude, and as it sinks, and it developed a sink rate of about 8,000 feet per minute or so, the wings started rocking side to side. They couldn't figure out what was going on. They were absolutely panic-ridden when you hear the voice recorder and so forth. And yet the stall warning indicator went off 75 times. From 38,000 feet, it hit the ocean, 3.5 minutes later, killed 229 people on board the aircraft. And this co-pilot insisted on keeping the pitch angle positive, even though the aircraft was fully stalled, sinking at that kind of a rate. You see the same elements: confusion, panic, fear. Aircraft was outside the flight envelope, didn't know what to do. Panic and fear, did the wrong thing, and lost the aircraft. We could look at many others. American Airlines 587. We could take a look at Asiana 214 going into San Francisco. Same kind of scenarios. And we'll talk a little bit about those as well. This doesn't only happen to the big carriers. The recent crash at Aspen, loss of control there again. Whole different set of circumstances. Even though the final NTSB report has not firmly come out, that is the initial indication anyway. So, what is this all about anyway? Why is this happening? Well, it happened because these pilots were put into a situation that they'd never been in before and they weren't trained to handle. And as good as pilots think they are, if they haven't been subject to the proper training, then they don't know what to do when the situation arises. It all starts with training. And the difficulty now is that we believe there's a critical difference between the way pilots should be trained and the way they're currently being trained. And it's going to get worse. If you listen to John Allen, FAA Safety Director, if you listen to people that are experts in the field, Mark Ralston, for example, they're all saying the same thing. There's about 34,000 new airplanes programmed to come online between now and the next 20 years, worth $4.3 trillion. We're going to need 430,000 pilots to man those aircraft, 69,000 in North America. If we're going to continue to train pilots the way we're training them now, loss of control is going to continue to be an accelerating problem. Let's look at some of the reasons why. We think there's three commonalities to this, and we just don't think this, but we believe that the insurance companies believe this, the FAA believes this, leading aviation institutions like Embry-Riddle believe this, and here's what we believe they are. increasing use of simulators, increasing reliance on automation, and lack of actual upset flight training and realistic emotions in the flight training process. And I'd like to spend just a second talking about each one of these. Now, I have nothing against simulators. I've spent hundreds of hours in simulators. I'm sure many of you have also. They're great procedural trainers. They're great for going through checklists and emergency checklist procedures, switch memory, and all that kind of thing. But there's no simulator in the world, none, that can emulate an in-flight critical emergency of an airplane in an upset condition and in a departure situation. A simulator behaves entirely differently than an aircraft behaves. You can do this all day long in the simulator. It's not going to teach you what to do in the aircraft. And yet more and more and more, we're relying on simulators to do the entire training exercise. And as we've seen in some of these accidents, the pilots then get to the airplane, they try to apply it, and they lose the aircraft. I mentioned the American 587, for example. That was an Airbus that took off out of JFK behind a Japan Airlines 747 and hit some wake turbulence. Co-pilot was flying it. The airplane started to roll. The co-pilot's reaction to that was to use the rudder to control the roll of the aircraft. The way he used that rudder was in a period of 7 seconds, he went stop to stop to stop to stop to stop 5 times and put such a vertical load on the tail departed the aircraft and they lost everybody on board. Why did he do that? Because that's precisely what he was taught to do in the simulator. He applied it in the aircraft. Didn't work. He also didn't understand VA. And by the way, that's another issue. A lot of pilots simply don't understand the certification requirements of their aircraft. They don't understand V-speeds. They don't know what VA is. VA, a lot of pilots that come through our program, you say, what's VA? They say, well, VA means I can do anything I want with the controls. Well, that's not true. VA is you can do a full deflection of one control and then back to neutral. Full direction of another control, back to neutral. Not this all at the same time. You'll put excess loads on the aircraft. It was not designed to do that. But simulators, again, they're great, but only as far as they go. They should not be used for critical in-flight training of upset and departure conditions. Increasing reliance on automation. I get into this habit myself. You know, the autopilots are great. Automation is great. We all use it. We all like it. It makes our job easier and so forth. We all understand that. But you know what I find the problem with automation is, one, if you knew how to fly aircraft before you started using automation and you use it too much, your piloting skills dull. You're not as good. You're relying on that stuff. If you don't know how to fly in the first place, you think this will fly for you, and you get into a critical situation and you engage the autopilot and autothrottles thinking it'll save you and it'll kill you. There's no autopilot or autothrottle system out there good enough to save you in a critical emergency or upset. I mean, look at, for example, Asiana 214 is a good example of that. Here's a 777 coming into San Francisco on a clear VFR day. There's 4 very experienced pilots on this flight deck, tens of thousands of hours between them all. And the VREF speed on that aircraft was 137 knots. If you look at the flight information, at 40 seconds prior to impact, the VREF speed on the aircraft started decreasing below 137. When it hit the wall, it was going 105. It means for 35 seconds, nobody figured out that the speed was decaying below VREF to 105. Now, lots of pilots in the room. When's the last time you were on final approach and didn't look at the airspeed every couple of seconds, right? These guys apparently didn't. And when they asked the pilot afterwards, why not? He said, I thought the autothrottles were controlling my airspeed. Well, they weren't, obviously. People were killed, the aircraft was lost, and a lot of people were injured. So automation, again, is wonderful. It's getting very sophisticated. But in every case we've seen with loss of control type incidents, When that automation fails and the pilot doesn't know what to do, they're going to lose the aircraft. Lack of actual upset flight training and realistic emotions in the training experience. I always like to preface this. Are there any former Air Force pilots in the room here? One? Did you go through Fairchild? You didn't? Okay. You were probably before my time. When I graduated from Air Force pilot training, we had to go to survival training at Fairchild Air Force Base in Washington. And you had to go there and pass it before you could go anywhere else, right? So for about a week, and there's a reason I'm telling this story, by the way. For about a week, they put you through ground school, and they teach you what to do if you got captured. And this ground school was actually developed by POWs that came back from Vietnam and laid out the whole program. This is what a POW camp is, and this is how you should be training people and so forth. Well, the second week, they put you in the middle of the Washington wilderness with a buddy like you punched out of an airplane. And your job is to get from where you are to a safe area so you can be picked up and rescued. And you have the stuff with you would normally have had if you bailed out of the airplane. And about 2 days into the program, you get captured. And you get put in a POW camp. And I got to tell you, you start wondering if you're really in the United States of America. It is brutal. It is unbelievable what they do to you in a 5-day period of time in this concentration camp. And after the whole thing was over, everybody took their graduation certificate and they went to the copy machine to make about 10 copies of their graduation certificate because they were going to put them behind every picture in the house so they'd never have to go through this again. And in the process of doing that, the guy that ran the school came walking in and I said, "Did we really have to go through all that?" And he said, "Let me tell you a story." He said, "We have found that if we're going to teach somebody a skill, and we cannot replicate the full emotional impact that's associated with learning that skill, you will never learn it to a degree of competency." That's why they did that to us. And I can tell you, if I got captured tomorrow, there isn't a thing I don't remember about that experience that I couldn't apply. Well, it's the same in this. In upset recognition and recovery training, you're in an airplane. You got to fly it. There's no simulation. There's no automation. You got to fly it. There's no hold button. You can't go out and get a cup of coffee and come back and reset it and all that kind of stuff. You're really in the aircraft. So we believe this kind of training is absolutely necessary to supplement what goes on with simulators to teach people how to be safe in the environment. Because someday probably, statistics show, someday probably, if you fly long enough, you're going to be flying along and something like that's going to hit you. We had a call 2 months ago or so from an MD-88 guy that said, you know what, who'd gone through our program, said, you know what, I was flying along and I hit some turbulence and the airplane went like this. And he said, I think except for your program, I'm not sure I'd have saved that airplane. So this, we believe, is absolutely necessary if we're going to improve the way pilots fly and the safety aspect of it. So all of that means we have a training gap, which is the difference between how a fully competent pilot should be trained versus the current training that has evolved. And part of this, as I said, we believe is URRT training. Now, what is URRT training? Well, the International Civil Aviation Organization is starting to develop parameters around this, and we're in the forefront of these discussions. These are some of the things that you do in upset training. And we actually put our students, depending upon what they're flying, in a couple of different aircraft. Importantly, aircraft that feel like the aircraft they fly every day from a control force perspective. You can't train somebody to drive a Mack truck if you put them in a Corvette. It's got to have the same feel. We do about 30 of these things. And the way we do it is, essentially, we show the students how the upset works and the recovery technique. and then we let them do it till they get it to perfection. At the end of the ride, we have the surprise element, which is whereby they're flying along and the instructor can put it in any combination he wants to at any time to see how the student will react to it. Now, what I'd like to show you is I want to put you in the cockpit. If you're a Part 91 guy or a jet guy, I want to put you in the cockpit and show you some brief excerpts about what this upset recognition and recovery training looks like. You're going to hear some, you're going to have a three-picture view of things here. You're going to see an airplane flying along. Most of these airplanes were filmed in an Air Mach-E 326, although you'll see a couple of Saberliners. You'll see one Saberliner example as well. There's a camera in the tail, there's a camera down the gun sight, and there's a camera that is on the student in the front cockpit. You'll hear the conversation going back and forth between the student and the pilot here, and you'll hear it kind of garbled because realize they're talking through an oxygen mask, they're pulling G's, so you may not be able to hear exactly what they're saying, but you'll get a sense of it. These recovery techniques that we teach are all relative to a process we call UTAP. If there's one thing we want our students to come away from, if nothing else, it's unload for control first and always. You don't power your way out of stalls, you unload. I could show you numerous evidence about why that works, and I could show you numerous evidence about why the FAA has been teaching it or promoting it wrong for years and years and years and years. You unload for control. An airplane aerodynamically will immediately start flying if you just push over. I mean, think about this. Let's say an aircraft has a stall speed of 100 knots, and you're flying along and something happens and the airplane departs. If you push forward and go to a half G, your stall speed immediately goes down by half. You're flying again. One of the beautiful things we show in one of our maneuvers is we take the aircraft up at about a 70-degree deck angle, and we get the airspeed really low, and we tell the student to push over almost to 0 G. And they see the airspeed indicator going down, 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 10, 20 knots. Airplane's still flying. Why? Because it has no weight. Weight, unload for control. It's the most valuable thing that we can teach. And once a student gets a sense of that, in any situation, if they unload, they will live. If the Calgon people had unloaded, they'd still be here. If the Air France guy had unloaded, he'd still be here, etc. So using this UTAP formula, which is unload, then at about 1.2 times VS stall speed, throttles, then ailerons, then pitch. Worst thing you can do, by the way, is when you're in a stall and the airplane's like this, try to use the aileron to correct it because you're going to exacerbate the wings that stalled and you're potentially going to go into a snap roll in the other direction. So you'll see UTAP being used here. The first one that you'll see is a simple stall on an Air Mach-E 326, and you'll see this pilot recovers just using the unload approach itself without any input of throttle.
Maybe 10 knots above the star, give or take. Set up. Okay, hold the nibble. 95. Starting the clock. Good. Very nice.
Simple stall recovery. On this one, which is an unusual attitude upset that you'll see, this is a 90-degree bank, slightly nose down. And you'll see how he addresses this one.
Lima 31, Edwards, Altimeter 3020.
New controls for my controls. Excellent. Good.
Okay, in the roll upset, you're going to see two roll upsets here. One, this becomes one of the most difficult initially for the students to do, although they get it pretty quickly. It's a fully inverted situation. And the natural tendency in a fully inverted situation is to pull, like that. If you do that, you're gonna do a split S and lose probably about 3,500 feet. The technique we use is to push, which is counterintuitive, push, and you're unloading the aircraft. So you're pushing up, you're rolling, and you're pulling. And if you do that correctly in a fully inverted situation, and remember the flight controls here and that they're using at these speeds approximate the way your business jet would feel. So the control forces are about the same. You'll see how he does this. He does it pretty well.
There's the start point. That's good. Rolling. And now I tell myself, okay, recover.
Show the little push there.
Well, about the same altitude loss, but I had a bit of a down vector when I started it, so.
This is what we refer to 160-degree rolling.
Slow, flaps too, so flaps coming down. Okay, rear controls recovered. Now push, and roll. Now pull, because as you transition that lift vector, keep it coming, keep it coming, keep it coming. That's it, nice job. Yeah, nice job.
Okay, this is where we show the difference between that push, roll, pull technique. And if you just pulled and did a split S, we want the student to understand the difference in altitude loss between the two. So this is a typical split S, and you'll see he loses about 3,500 feet in doing it this way.
A couple thousand feet. Okay. Yeah, about 3,000 maybe. Okay, so what you did is it idle. I'm ready to flow. Yeah, go for it. I'll get the horn. Thank you. We're starting at 13.8. But you have that as advertised at 10-3, 3,500 feet. Okay.
Okay, so that's a split S. This is not so much a necessary part of upset recognition or recovery training, but it's neat to be able to do it because about 65% of the pilots that come through our program, one, have never been upside down in a jet, so this is a new experience for them, and two, they've never not only spun a jet, a lot of them have never spun anything. So they don't know how to, they don't know what they would do if they potentially got into a spin situation. So we teach spins not as much as they're going to be a typical recovery technique, but just the confidence that it builds in the student from getting into a spin and recovering. This is an upright spin that I'll show you, a 3-turn upright spin. There's variations of this spin. You can do it with the ailerons neutral. You can do it with the ailerons pro into the spin, which creates a more rapid turn. You can do it with the ailerons against, which creates a flatter spin. And we can do inverted spins as well, which some students like to see, which is very, very interesting as well. This is a simple 3-turn upright spins, aileron neutral.
Okay, there's a star there. Good inputs. So at 19. We'll call out stable there. There's 1, 2, and 3. Okay, and recovering. Nicely done all around.
Okay, this is a Saberliner part of the course that we teach. A lot of the folks that come through really enjoy the Saberliner experience that they get because that is actually a business jet, which is just exactly like what they fly. But one of the things we teach is stick shaker flying. In other words, if you had to max perform that aircraft in a microburst or something, and you wanted to get max performance out of that aircraft, you would apply power, you would pull the pitch angle back until you were just above a stall. You know, a stick shaker goes off typically 5 to 7 knots above a stall. They're going to actually get a stick shaker here, and they're going to fly it with the stick shaker to max perform the aircraft.
There it is, adding the power, holding what I got, flying it out on the tickle. So far I've lost 40 feet. There's 50. Starting to get some acceleration. Pointed airspeed here, we barely still just got back to 120. So we're okay on the altitude per the old style, but it takes forever to get away from that bad spot.
Okay, so that's an example of the kind of things we do. There's actually 30 plus maneuvers that we do. The students all get a video much like that they can take home with them and review the performance that they did and so forth. They can hear the instruction going back. We like to make the point that aerobatic training, while helpful, is not upset recognition and recovery training. First of all, there's no startle and surprise element. The control forces in an aerobatic airplane are very light. So you go like this, the airplane goes like that. That doesn't happen in a business jet. It's completely different control forces. You're flying, an aerobatic maneuver is a controlled maneuver within the flight envelope, and it's controlled throughout the process. The procedures we teach, obviously, border on the edge of the flight envelope, sometimes depart the flight envelope, and there's startle and surprise and all of that goes along with it, just like would happen if you're in an airplane and you're flying along thinking you're going to have a good day, and you hit wake turbulence and boom, you're not having a good day. So same kind of emotional play. So in summary of all of that, the way we believe, and many are starting to believe, that this training should be accomplished is, first of all, a very thorough ground school, briefing on certification requirements of airplanes, how the airplane should be flown in an upset scenario, all kinds of information that surround that. Go to a simulator, which is great for the standard procedures that you would use a simulator for, checklists, emergency checklists, switch memorization, and all kind of that kind of thing. But then do the actual flight training in an airplane without automation, without simulation, and teach these maneuvers thoroughly so the student gets it, understands it, knows how to do it, and will be able to do it in the future if the conditions should so occur. And we think the selection process, when we talk about URRT, these are the things that we do that we think are important. And we now have 4 major insurance companies that are backing us with this. Embry-Riddle University, which is the largest aviation university in the world. They say that about 1 every 5 people that graduate from Embry-Riddle is in the aviation world. So if you're running to 5 people, probably 1 of them came from Embry-Riddle. We have just been selected after a very exhaustive search to develop upset recognition and recovery training for all their undergraduates and their graduate students we're going to be doing in Mojave. And these are what we think are important. We own our airplane and we maintain our airplane. We have 45 aircraft in Mojave, and we have our own maintenance crew that has been there forever and takes care of these aircraft. So there's never an issue with safety, maintenance, any of that kind of stuff. We know exactly what's going on with it. In our program, the student flies. We don't just demonstrate to the student flies the aircraft. We've had people come through the program and say in some other situations they've been in, it's sort of a demonstration ride, showing them this and showing them that. In our program, our students actually fly airplanes. We use the aorta and ICAO maneuver practices that are being developed, and then we exceed those by a multiple. Very importantly, we use aircraft that are like the aircraft that our students fly every day. If they fly prop airplanes, we have a course for them using prop airplanes. If they fly turboprop airplanes, we have a course for them using turboprop airplanes. If they fly jets, we have a program for them using jet aircraft, because those are the aircraft that look and feel and perform like the aircraft they fly every day. Those are the kind of aircraft they should be trained in. We're very, very proud of our instructor qualifications. I could go on and on about the guys that we have teaching this program, but we have 2 former astronauts on our staff who are both, one is a naval test pilot school graduate, the other's an Air Force test pilot school graduate. They both taught at those schools. All our other pilots are test pilot school graduates, combat veterans. I think I counted our instructor staff has something like 87,000 hours of flight time among them all. They've been doing this stuff for years, and they're very, very, very good at it. So we're very, very proud of that, and we think all these things add up to a very compelling story that we have to tell at Flight Research. So thank you very much for your attention, and I'd be happy to, by the way, we have some dessert up here too. Why don't you grab some dessert? I'd be happy to answer any questions that you may have about any of this.